Last lesson we looked at stationary points and how to hunt for them. Today we'll look at the different types of stationary points, and we've already alluded to these three different stationary points. So on f of x, that's this graph here, what we've got is a being a local maximum. So that's a local maximum. Note that it may not be the absolute maximum. The absolute maximum of the function, assuming that this continues indefinitely to positive infinity, is positive infinity. But locally, or around these parts, this is the highest value, this zero gradient point. So we say that this is a local maximum, not the absolute maximum, or not the maximum value of the function, just locally or around here, this is the highest value. The local minimum, well, B is what we call a local minimum, because around this sort of area here, this is the lowest value it can produce. It's not the absolute minimum, we can see that we go lower here, but it is the local minimum. And finally, for point C, we call this a stationary point of inflection. So what happens is the positive gradient gets smaller and smaller and smaller, becomes zero there, and then gradually increases once again. So we say that it is a stationary point of inflection. So we've got a point of inflection here, and it in fact does go stationary. That is that the gradient at this point is zero. All right, so the task will be to sketch the graph of this cubic function showing the x and y-intercepts and stationary points. And further to that, what we're going to do is draw up a gradient table to help us describe the nature of the stationary points. Okay, so let's get the x-intercepts first. So recall that the x-intercepts, so let's go let y equal f of x. We're going to say that f of x equals 0. So this function equals 0. This allows us to use the null factor law. Note that I'm avoiding actually rewriting the function here because it's already to go, so I don't need to rewrite the function. I'm just going to say if y is f of x and f of x equals 0, then I can say x equals 0 and x equals 1. Now recall that because that one there is squared, something interesting happens at this point here, and we'll remember that it's going to turn on that point itself. This x equals 0, 1, that's just your standard x-intercept. Alrighty, so now what we need to find is the stationary points. Alright, so remember in the last lesson what we did was we found the gradient function and then we let the gradient function equal 0 to find stationary points. So I'm going to do the same thing with this one here. So we actually don't know how to derive a function in this form yet. We can do it next year, but actually in year 11, what we need to do is expand this out. So we'll say that f of x equals x multiplied by, and I'm going to expand the perfect square. And then go f of x equals x cubed, take away 2x squared plus x. All right, so now that I've got it in a form that I'm willing to derive, I'll get my derivative or gradient function. All right, now what we get is the derivative for a cubic will be a quadratic, and that seems to make sense because cubic functions, a lot of them look like this, which means that we're expecting two stationary points. All right, now I am expecting a stationary point here at x equals 1 because that was the repeated factor, and I need to get one somewhere else, somewhere other than 1. So let's find out where it's going to be. So if this is my derivative, let's let the derivative equal 0. And how do we find out when quadratics are equal to 0? We attempt to factorise using the null factor law. Okay, so that is 0 equals x take 1, 3x take 1. So what it's got is a 0 gradient point at x equal 1 and x equals a third. Now that does make sense to me because I knew that would happen from here, but it's good that calculus also has identified that that x-intercept is also a stationary point. So I know that the y value when x is equal to 1 will be 0, okay, because I know that it turns on that x-intercept. Now I just need to get this one here. So if x is equal to a third, what I'm going to do is bang it into the original function. I'm going to put it in this form of the original function. 1/3 take away 1 squared. That is 1/3. That's negative 2/3. And we square that, which becomes 4 over 9. That's 4 over 27. All right, so our stationary points occur at 1, 0 and 1/3, 4 on 27. Alrighty, what else do we need? We know that it goes through the origin, so we don't need the y-intercept, or we know that that is the y-intercept as well. So I think we've got everything we need to sketch the function. So let's draw up a Cartesian plane. And let's pop in our values. So here is x equals 1. Here's 2/3, here's 1/3. Alrighty, now what I know is that it's a positive cubic, so positive cubics start like that. What's going to happen is it's going to cut through 0, turn here, come back and loop around there. So let's just see if I can draw this in one big hit. That's not bad. Okay, so there is my cubic going through the origin and topping out at this point here, this stationary point here is 1/3, 4 on 27. Alrighty, so let's have a look now. Our diagram tells us what the nature of the stationary points are. So I know that this 1, 0 stationary point is a local min. I can tell that off the graph, so I can see that. And I know that this stationary point here, which is this one here, is a local max. Now sometimes, and in particular in the Year 12 exam, they actually give you a function that you're actually quite unfamiliar with. And what they do is they get you to do some of these substitutions to give you hints about whether your maximum's a local min or a local max and things like that. So you actually may get functions that you don't really know what they look like. And so a method to find out the nature of the stationary point, that is whether it's whether it's a local max or a local min, is to actually use this particular strategy here. What we do is we draw up what we call a gradient table. So we start with x, then we go f dash x, and then we go shape. Now what we're going to do is choose 3 points to present this. Now one of the points, so just say I don't know what this is. I don't know whether it's a maximum or a minimum. So what I'm going to do is starting with x equals 1/3, I know that f dash 1/3 is going to be 0. That is, the gradient there is 0, and 0 gradients look like that. All I do now is I choose a value to the left of that and a value to the right of that. So the value to the left just seems to make sense that it's 0. Alright, so now I need to do f dash 0. Now my gradient function is here, and I pop 0 in there, 0, 0, 1. So f dash 0 is 1. And that means that there's a positive gradient there. Now what I need to do is get a value to the left, to the right rather, of 1/3. And I could use 2/3, I can use basically anything here. I can't use 1 or more than 1 because I need to know what the gradient is to the right of this before the next possible stationary point. So I'm going to use, and I'm going to find f dash 1/2. That seems to be the easiest fraction to work with. Alright, so here's my gradient function. It's 3 times 1/2, and that's squared. Take away 4 lots of 1/2 is 2 plus 1. Now I know that this has got a negative gradient over here because I can see it from the picture, but just say we didn't know what the function looked like. There's going to be functions that you don't know what they do over here because of the way the function looks. So let's just work it out. So this is 3/4 take away 2, which is 8/4, plus 4/4. Okay, so that is going to be 3/4, take away 8/4 is -5/4, plus 4/4 is -1/4. That's -1/4. And that's a negative gradient, so we draw this shape here. And what we can clearly see is the shape says it goes up, or it's got a positive gradient, 0 gradient, negative gradient. And that means that we can tell from that that we've got a local max. Okay, local maximum right there. So that's what we call a gradient table. Okay, and we don't need to do it for cubics because we know what cubics look like. We know that positive cubics max and then min. We know that negative cubics min and then max. We know that upright parabolas min. We know that inverted parabolas max. So for a lot of the polynomials that we've worked with, we know actually what is going to happen, and we don't need a gradient table to help us. But remember, as I said, this process, you might think, well, what's the point? Well, the point will be that when we get a function that we don't know the appearance of, or we don't know what it actually looks like, we don't know whether it's a min or a max or a stationary point of inflection, that these gradient tables actually help us considerably. You can do all of this on the calculator, so it'll be a speedy process to actually punch this function in and to get your derivatives with the calculator. So I'll just run you through that process one more time. So we define our function, shift 7 for define, f of x equals x multiplied by x take 1 all squared. So this would be for an exam 2, all right? And you should do some of the questions with the calculator just to make sure you can do these moves. So the first thing I did was obtained the x-intercepts. So that is a solve, so shift equals f of x equals 0 for x, and that confirms that I was right on that part. The second thing we'll do is diff it, so shift negative or subtract, and we'll diff the f of x function to get our derivative function. Now remember what we do is we go shift ants, sorry we don't do that, we do shift equals solve ants, so shift exe to get ants, equals 0 for x. And what that says is, hey, that expression for the derivative, when is that 0? Tells us that we've got a 0 gradient at these points. Now remember then what we can do is just shift 8 to get f of, we do f of 1, that tells us the stationary point is 1, 0, and f of 1/3 is 4 on 27 as we found out. You can also use the fmax and fmin features of the calculator. They are quite handy features. But you need to know a little bit about the endpoints of the function or where to search for the local min and local maxes. So that's the only caveat to using those. The final thing is we'll just show you how to quickly get a gradient table. So we can go f of... we can go the derivative, so I'm going to take this, shift comma to get the pipe or the with key, x equals 0, tells us that I've got a positive gradient at x equals 0, and this will just confirm that we've got a negative gradient at a half. Okay, so this will just help you with quick substitutions to work out whether it's positive or negative. And of course, at x equals 0, the gradient is 1. X equals 1/3, my bad. The gradient is 0. So that just confirms what we did in the gradient table. So there's some handy ways to do that on the calculator, and you should do a fair few of the problems. You'll go through this sort of 5-6 step process in year 12 just so many times. So better to get used to it now.